So welcome to, officially, how the challenge of deploying Mesos revolutionized the way we use SaltStack, or as I've been calling it, Mesos is a harsh mistress. In this particular talk, it is going to be a case study of SaltStack's role in an Apache Mesos deployment. Another optional subtitle might have been how we broke SaltStack to do this. So there's going to be a lot of Salt stuff. It doesn't require tremendous familiarity with Apache Mesos. It does require familiarity with Salt because we're going to move very fast. There are a lot of ways in which we broke Salt, and I want to give a 10,000-foot view of all of them. There will be code samples. Familiarity with formula paradigms will also probably be pretty helpful. And they're going to be chock full of references to Heinlein's Moon is a Harsh Mistress. Let's see if there's anything else. Oh, yeah, and if you do have questions, because we're going to move through this really quickly, I'm going to be hanging out at the Virtustream booth, and we'll be taking sort of extended questions. I'll have my notebook with me if you want to see more code or you want to get a second glance at stuff. And I'm sure slides will be made available by some means afterwards as well. So about me, my name is Chad Heuschober. I'm Principal Software Engineer for Virtustream Platform Engineering. I'm a professional wearer of hats. I have been a software engineer, database administrator, automation engineer, just about everything but a straight sysadmin. I'm also a SaltStack veteran. I have been using SaltStack, I know, since Aud 11. I think before that as well. I'm SaltStack Certified Engineer number 12, and I'm personally an author of around or slightly above 115 custom modules and or formulas, very few of which are public, but that's just the nature of it. So about Virtustream, most of you have been at the general session. You've probably already seen this slide. We do big stuff with other big things. We'll move on. Oratory is a null program here. In late 2015, our platform engineering team took the challenge of deploying a massive customized logical compute cluster based in part on Apache Mesos, and it was spread across a dozen data centers. And we had a lot of constraints. The first constraint was we had a really limited deployment window. When you consider when hardware's coming in, when the base stuff is going to be provisioned, and when we have to be delivering services to our customers, that window's really tight. And so automation ahead of time, knowing that we had these goals to meet, was a primary concern and driver of what we were working on. We have complex interdependent services in a Mesos stack, where there are issues with a lot of services that are quorum-based and clustered, and delivering the ability to architect and integrate clusters together is a huge piece. Their Bootstrap states as well are sort of related to that. So things that come up in a different state than what you would want to maintain them at. And then service health and readiness are also real concerns. So this is, I don't know, like a 10,000-foot view of our platform with some of the interdependent services. There's a lot that's actually redacted here. What's missing are the several components that go into our software-defined networking layer, which would include etcd and Calico. We're missing all of the logging and the metrics pieces from this diagram. It is already complex enough that it's a little bit scary when we started diagramming this out and thinking about how we were going to put all these pieces together in a tightly interdependent way that is also still going to use formula paradigms that enforce best practices in automation. If we just were to list out some of the components, this is maybe 60 to 70% of the stuff. We've got Calico, Consul, DNSMass, Docker, etcd, Marathon, Mesos, Consul, Salt, Zabbix, Zookeeper, and a whole bunch of other things. Also notably, we have quorum-based services here on 3 of them, which are their own challenges. So where we start this is where we already were. The Virtustream team was already really strong in SaltStack automation with our formulas. We wrote a ton of them, as you saw in Stephen's keynote, and we had great work with execution modules and state modules as well. We had a lot of people who were very competent in that. So we approached this thinking, all right, we're going to salt it the way we normally do. But immediately some issues were made evident. So first off, the clusters were difficult to and or slow to test independently. So we use a vagrant box whenever we test our formulas, and we use that for development of the formulas as well. But bringing up a vagrant box, for one, takes long enough. You bring up 3, it's much longer. And if you're bringing up the number of services you see here in vagrant boxes, it's impossible. It's impossible for a developer to reasonably wait for 60 minutes to come back to their machine and see whether or not any of their states worked. And if any of you have developed formulas or states, you know they rarely work the first time you write them, right? So existing formulas, so that was an initial problem. Another problem, existing formulas had dependencies in the context of this stack only. If you were in Charles Radetzky's talk, he talked a little bit about the wrapper formula concept. I'll go over that again here. We have bootstrap states that, as I mentioned, these differ from maintenance states. And then also services are not always ready when service.running comes back and says they're ready, right? So we had a lot of challenges to work around that. We're going to cover all of this in this talk, which is why we're going to fly. So addressing cluster tests is where we're going to start with this, because it's sort of the first piece. And I'm going to have a logical progression through these different components. As we encountered each problem, I'll talk about some of the ways we broke SALT to make it work. So the cluster test was an easy one for us. We just sort of logically extended our formula paradigm. And instead of doing one vagrant box that was itself just a masterless minion and then testing the formulas in that, we actually made a vagrant box and added salt cloud and LXC into that vagrant box. So the salted vagrant image itself was a master, and then we had LXC minions inside it. Well, why did we do that? Well, like I said, it's much faster than multiple vagrant boxes, and it's faster to deploy and destroy and just keep testing and getting it to where we want it. And it does have some challenges that are not perfect, but adding salt cloud and LXC produced a lot of win for us. So, to go back here, just sort of going through the way that the code block looks. We've got this is the LXC providers bit, so we just basically say we've got a provider that's LXC. Moving on, we set up the profiles. So we set up an Ubuntu profile that just basically is an AMD 64 image, and we point it at our master, which is the vagrant box itself. Then we do a map file here, and we set up, just tell it that we're going to do 3 Zookeeper nodes in this case. And just a little bit of an aside, I'll probably use, I think in this, I mostly use Zookeeper and Mesos for my descriptions, but the same paradigms apply to a lot of different pieces of the stack. I'm not going to tell you about how we did etcd, Zookeeper, Marathon, Mesos, Consul. We're here to talk about the big concepts and what we're doing with SALT. So we set up the map file. And here's where some more magic. So this is in the pillar where we can define LXC, where we can define container profiles, right? So the LXC Salt Cloud option lets you define in pillar some of the various configuration of those LXC profiles. And this right here on line 18 is actually where a lot of the magic happens. The reason this is so successful for us is because by using OverlayFS, we can snapshot an existing salt minion pre-seeded LXC template, and then in about 5 seconds, I've got a minion. And that allows us with the Salt Cloud runner able to basically deploy these guys in almost no time at all. Right? So this solved the issue of clusters right away. Now we've got a cluster of 3 machines. Or more if I want it. They cost me almost nothing in terms of memory or disk space inside my vagrant, so I don't really care that much about performance. And this is really just to test that the formula states that I'm applying are indeed going to apply to clustered paradigms. So the next step was allowing these services to discover each other. Most of you who know SALT probably know the first place to go for that would be the mine, right, to share the information. There are a few little tricks with the mine that were problematic for us there. Mine utilization needed to be optional. There were cases where we wanted to statically specify discovery information. There are cases where we wanted to use the mine. It's not exposed in the pillar. If you're building formulas, using the mine is a bit of a dangerous case because the whole point of pillars is to expose all of the elements of control and pieces of control that you want in the pillar. But the mine itself is not exposed in the pillar. It's only called from on the minion side, and the pillar compilation is happening master side. And then mine functions that are used for discovery might actually differ from environment to environment or state to state. So the first thing we do is we set up the mine functions in our pillar, which is pretty standard fare. You can define mine either in minion.d config, or you can define it in the pillar. And as long as you do a pillar update, and a mine update, sorry, it'll discover these guys and it'll load them into the mine. So in this case, I'm defining here at line 2 Zookeeper hosts, and here at line 5 just some mine functions, Zookeeper hosts and Zookeeper IDs. And then in this case, this is a pillar.get, and this one is a network get hostname. Now, I do something a little bit, I don't know if you call it clever or perhaps really scary. I've defined a new key inside my Zookeeper formula that I just call mine calls generically. And we actually ended up using this paradigm in a lot of different places, where I've basically just given a name and a key name and then exposed the mine functions. And then I do a deferred execution in the map file. So in the map file, I have a little mine data here, and I loop through all my mine calls, and then basically run them, passing them each of the parameters that we define. These are the same ones that you would find in mine.get, and then just do an update on those results. And then later, you can see that I'm able to pull in this piece right here at line 6, and I'm using the mine data in my formula. So this deferred execution, and if we sort of just dial this back a little bit here, we note that the function name here, Zookeeper hosts, is the same one that I find here on line 2. So this all sort of ties together, allows me to use the mine in our formulas in such a way that I can change all the relevant pieces as I need. It's optional inclusion because I can choose to use the mine data that I generate or not, and it can be there or not, and it's just it's a great way to go forward on that. So some formulas, so that solves that problem. Now, some formulas have distinct service layers. A great example of this was, I think Mesos, is that the one we're using? Yes, Mesos. So Mesos has a master service and a slave service. And if we're thinking about it how we logically construct them, the master and the slave share some configuration elements between them. They share a Zookeeper pointer and a few other pieces. So I don't want to repeat that when I'm building my formula, but at the same time, I have these service layers that are sometimes interdependent and sometimes not. There are reasons why I might want to run a Mesos slave service exclusively on a node. There are reasons why I might want to run both on the same node, and there are reasons why I might want to just run a master. So these service dependencies need to be optional. And this is where the idea of wrapper, or what I often call metastates, comes into play. So this is what a standard formula tree looks like with some pieces redacted. We have the map.jinja that most of you are familiar with. We have a templates directory where we've just got file templates. We have the slave directory where we are configuring our Mesos slave. A master directory where we're configuring the Mesos master. And here at line 3, we've got our common pieces that are actually shared between both of them. We're going to ignore lines 15 and 16 because we're coming back to them soon. So this layout here, pretty standard. It's a great way of segmenting the service layers. But notably at like line 19 here or line 13, we have the init file defined. And that init file, in these cases, never, ever carries within it actual state data. It's never carrying states that I've defined that are doing anything. This wrapper or meta state actually just does an include extend pattern. And the include extend pattern allows me to just pull in the pieces that I want and then extend them to established dependencies. This also helps me develop my formulas and test my formulas because I can do state.sls on every single file that I have in a state tree and know that it will run without complaining about dependency problems or running all the other states. So if I've already done an install and I don't want to do a Mesos install again and I just want to test this one configuration element, I can use state.sls and throw that together. So the include extend pattern may be a little bit ugly to read, but it allows us to set up interstate dependencies and also between different service layers. So if I go one step further to the top level Mesos formula init, you can see that I've included just the master and the slave, which themselves, as we've count it here, do the various files that they need to. They pull in everything. So the slave service is complete as of, or the master service here, yeah. The Mesos master service is complete as of its init file. By pulling those in, I can just set up the requisite chain between the slave service and the master service to ensure that the master service runs, or the slave service runs after the master service. And then I can do all of these state calls independently, or it pulls it all together here in the top level Mesos init. So this construction is a part of the solution, but it can be extended a little bit further. Anybody here know why a laser beam is like a goldfish? It's because neither one can whistle. Okay, so some common formulas also presented new dependencies in the stack context. So the reason I just showed you this interstate dependency stuff is because it can work across formulas, right? So we have Docker and FluentD, and if we're using the FluentD log driver of Docker, I now have a hard dependency on FluentD being present before I can go forward with starting Docker. So this is a pretty good example, I think, of how we might want to establish a dependency between those formulas. So we can use the include extend paradigm to go ahead and do the same thing with existing formulas. The only difference is we're not setting up a single state somewhere else that wraps them together. We're not putting something in serve salt that is a normal state. Actually, we're going to use an orchestration state to go ahead and do that. And the orchestration state has a few caveats. The first is it requires that I already know my targets. And this is going to cause other problems for us that we solve later down the road. But one of the things of state.orchestrate is it has a TGT, a target parameter, and you have to tell it where you want it to run this. The other thing is that the orchestration metastate sort of requires buy-in across the platform. You know, that everybody else is also providing an orchestration state so we can pull them all in together. And then it kind of effectively deprecates state.highstate. And I'm not sure that that's a bad thing, actually. They aren't all bad things, and it can open up a lot of new possibilities. So we're back to this guy. This is the same one you saw earlier, just the tree of the Mesos formula, like I said, slightly redacted. And we're going to look at lines 15 and 16 here, where I've got just a little orchestration folder and a Bootstrap. Inside that are a couple state.orchestrate calls that use the SLS parameter to just call the individual master state and the slave state. And if you see at line 13 and 14, I've set up a requisite between the slave state and the master state. Now this is kind of duplicating what I did in the init, but the difference here is I'm allowed to target different nodes. So whereas the top level Mesos init is great if I am putting both Mesos master and Mesos slave on the same host and I'm applying that state, this allows me to break it across multiple nodes and still ensure that I have requisites chained, and even that it will stop orchestration if it encounters a failure, which is a huge part of what I want to do, because if I've got a problem, I don't want to just order things quickly. I want things to stop, and so I can figure out what went wrong partway through my orchestration. The yeah, lines 5 and 12 have the individual states. There's an interformula dependency here at 14, and we'll talk about targeting very soon. And the other reason is, you see I call a lot of these bootstraps, mostly because I want to leave the door open for more stateful, state machine-like execution. And so as the orchestration evolves in this process, if I want to have a different state that I use for maintenance, then I'll maybe create a maintenance state or other states that I want to use for that. So I just called them Bootstrap. That way it keeps the door open. And then here's a wrapper for all of these guys together. Again, if you saw Chuck Radetzky's speech, you probably already saw these pieces. But we've got an inclusion here where we include this orchestration high state. This one is a real killer. I'll talk about that in a second. Zookeeper and Mesos. Again, our normal state that looks like this is 8 times as big as this is, but I wanted to just make it slide-sized. And we just do an extends, and we do the requisites in the extends, and it all ties together. So the orchestration.highstate that I talked about, this was a generic state we ended up creating that is just super clutch for us. All it does is really simple things like, I don't know why this doesn't happen all the time right before I run states, but it just does a sync of the modules, does pillar refresh, does an update of the mine, and make sure it does those in the right order, because if you don't get the order right, it's not going to do what you expect it to do. And then it does a high state. And in this case, I said we deprecated high state, kind of. Well, we deprecate high state for our application layer, but for our like base OS layer, it's actually still great for us to use high state for things like making sure NTP is there and SSH is there. But when we start talking beyond that, and we're talking about our complex service layers, we've really gotten rid of using high state to maintain them because we can use our orchestration states to do the same. So let's see. One of the challenges with moving to orchestration in a really big heterogeneous environment is the targeting. And I said we'd get back to targeting. So the minion ID globs are totally useless to me at this point because I can't guarantee that every data center is going to have nodes that are named the same. And instead, we turned to Pillar and specifically just created a roles paradigm where we define roles statically in the Pillar, and then we target them. So let's see, what do we have here? We've got the, what am I looking at? Oh yes, the Bootstrap SLS for the orchestration. We have the target for the roles here on line 3. And we just set up a fairly deep chain on the key. I found that 3 levels deep tended to make sense because the second level, the Mesos, is going to be the formula level. One step lower than that is the service that we are exposing or we want to target. And then I enforce true just in case somebody else wants to set false in a pillar merge case where we've got multiple pillars coming in together and somebody needed to set it off. I want to make sure that I actually can merge. So just the presence of a key is not enough in my book. I actually want to get an explicit true or false value. So here's what the roles look like. So we set up in serve pillar, we've got a roles folder, and then we just start setting up our roles here. The roles will include the pillar for the service lines. So if we've got a Zookeeper pillar that we want to include, that will get applied to all the Zookeeper nodes. I actually include it here. And I do the same for like the Mesos master in this case. If I'm running Mesos master and Zookeeper on the same one, then I use the roles key to set up whether or not we've got Zookeeper, master, slave, et cetera, and I set these values here. And here's an example of doing it with a slave where I'm just including the mesos.slave pillar key and doing a roles mesos slave true, and that's the only role that this one might have in this case. The pillar top file then becomes really quite simple. I just point it to the roles. And since the roles are already containing the rest of the pillar tree for that given profile, it's actually a really bare and clean targeting engine, right? Now I don't have to go looking around and wondering, did I make sure that I applied 6 blocks up or 20 lines up, which part of the pillar needed to go with which of these? It's really straightforward. I look in my role, I see my role, it's included everything. Great, moving on. The other neat thing about this, the other neat thing about this is because I've gone ahead and included the roles in my orchestration targeting, I don't need a top file for the master either. And the part of that is just because all the role targeting deprecates it in, right? So we look at the, I'll just go back here. Here. The targeting is happening on pillar if I define the pillar top as having this data, then I don't need a top file really for the master outside of what's being applied normally in sort of like our base OS maintenance stuff. So the orchestration also had a really a neat side effect of allowing us to solve the Bootstrap State problem. I mentioned the Bootstrap State problem as being a case where some services may need to boot in a slightly different state than how we would maintain them long term. Great example of that is Consul, which has a Bootstrap expect parameter that I use to cluster together multiple nodes. When I pass Bootstrap expect to Consul, it's going to wait. We give it an integer. We say 3, 5, whatever. It's going to wait to actually start the service until all of those nodes have come up, and then it will cluster them together. If I pass Bootstrap expect to a subsequent run of Consul, it puts it back into a Bootstrap state and destroys my cluster. So I don't want Bootstrap expect to stick around after my initial orchestration. I want it to be there when I first bring it up, then disappear. So the pillar parameter of salt state is a really useful part of that, because during the salt mod state command, I can pass pillar, and that will inject any pillar I want into that state. The downside or caveat of that is that it actually doesn't do any form of merging and will do a hard override of that. So we have to be careful about what we call that. In this case, I've done a top-level new key that I'm just calling Consul Bootstrap true. And then my formula knows how to read or look for that particular pillar key. If it's present, it adds the Bootstrap expect parameter. If it doesn't, it goes away. So here, at line 1, I start a state where I basically set up and I do a config on Consul. Assumedly, I've also installed it probably before. Again, these are slightly redacted. But I'm doing my configuration management, so I'm now setting the config file. It's adding Bootstrap expect in there. Now I do a server start, and it will start the service. The Bootstrap expect will do what it does. And now, after the fact, I go ahead and I do a SLS Consul config again, removing the Bootstrap expect, or the Consul Bootstrap true pillar key, which means that it doesn't get set on, and the configuration reverts to the state at which I wanted it to be for maintenance ongoing. And the only difference between these two really is this little pillar injection that I do right here. So as we neared the end of the deployment, we realized that some of our services needed to also run on top of our platform, right? We're building a compute platform, and it makes sense that some of the services, like Mesos Consul or Mesos DNS, would actually run on top of those pieces, namely our marathon scheduler. We started off writing a super slick marathon state module that basically manages applications on top of marathon. But deploys continued to fail because marathon wasn't always ready when it said it was ready, right? So service.running comes back true. This is pretty standard with Java stuff, right? We encounter this all the time. Sometimes you sleep, and you never feel good about it, because you can't guarantee that it's going to be done when the sleep's over. Other services had issues like this. So we needed a health check module that could act as a semaphore. I much prefer having a true semaphore. And so instead of failing immediately, then we could retry the endpoint a set number of times. So we made one. The health check module just takes in basically, in this case, I'm demonstrating the definition for the HTTP side of it, but it's got other calls that we make. And it just runs off and does a health check against a service endpoint. In this case, it's going to either look for statuses, have a number of temps, potentially do a sleep on its own, or we can even dig the return value and look for a specific key and an expected value. And Salt has some great dictionary traversal things in utils that I use for that, and I really recommend you go find them. Unfortunately, it's really hard to find stuff in Salt utils, and hopefully that will get solved as Salt gets better. But there are some really cool dictionary traversal things that let you just go find the key you're looking for in a big dict. So yeah, that's that. And then the health check module itself works just like this. We just make a call. We go to our endpoint. We set the number of check attempts. And eventually, it comes back and tells me it was healthy after however many attempts it had to make. This was really key. So we started adding this health check module then in between some of the services that we knew were not immediate bootstrappers. And we just wait until they came back, and we can guarantee that they were healthy. Once it came back healthy, orchestration continues. So this then becomes a state within our larger orchestration context. Let's see. Oh, yeah, this is fun stuff. OK, so many of the applications were quorum-based. And that means maintenance cannot use anything that even remotely resembles a high state where every node is going to get rolled at once, right? And the what's it called? The batch mode, right? Doesn't guarantee that I have restored my quorum before it goes and rolls the next node. So state.orchestrate didn't yet even have support for batches. I have questions as to whether or not it's going to guarantee me it'll fail out anyway. And a for loop is easy enough, but weirdly, there was nothing exposed within Salt that let me get a list of minions that just met a match criteria. So if I wanted to use a glob matcher and I just want the minions back from that, I can use test.ping, but it doesn't actually just have it exposed at a data layer where I could just get that as a proper list or otherwise. So we made a little match module that actually does that and runs off and takes the target at the expression form and whether or not we want to include the actual status of that minion or just the fact that it matched that minion. And that's kind of what it looks like. So we will do match minions. And this is an important part of things because we specifically need it to be a runner. We need it to be a runner because we're going to use it in orchestration context so that we can roll nodes one at a time. I need to be able to use salt run. Since the salt orchestration engine uses an instance of master minion, that instance is pillarless and basically absent of anything useful. So here's what it looks like in the end. We start by setting a runner here at line 1. And this is just actually literally returns a runner instance. And then we go ahead and get the minions using our little match minion. Once we've got the minions, if there are any, we roll them, and then we do a new state, an orchestration state with a loop index, right? So since we can't have name clashes, we set the target to whatever that minion was. And then if it's not the first, we actually make it dependent upon the prior. That way, it'll fail out if we encounter problems, and at least, hopefully, we've only lost one node. Let's see. The last piece of the rolled maintenance problem was being able to call state.orchestrate from within the context of orchestration. This was largely because, as you can note, as we move more and more towards our orchestration as libraries or states that we want to maintain, we start to want to use them as building blocks or pieces within each other. So turning orchestration states into callable state routines is a fantastic thing. And it also helps us avoid the implicit simultaneous execution. So here is here's a great little thing. We made a salt orchestrate. We basically forked salt mod and added a little orchestrate command into it. And now we can use salt.orchestrate to call other orchestration. The only thing that was really challenging about this one is reading the result set and actually determining whether or not you were successful, because state.orchestrate still doesn't have a great way of determining success after the run. You can go dig inside it, but you have to do some recursive things to make that happen. So that was probably the biggest challenge here, was just doing the recursion on the return from an individual orchestration run. And then now we can basically call orchestration inside orchestration and use our orchestration salt mod states as the same as we would with anything else, and just sort of mix and match and piece it together. So there ain't no such thing as a free lunch. When all these advancements were combined, it reduced the total effort we had to, the estimated effort we had to deploy data center to about 0.6% of what it was originally. Or in other words, about 4 days down to 15 minutes. We can deploy an entire data center in that time frame now, sort of irregardless of the number of nodes. We had tons of stumbles and false leads along the way, but the provisioning and maintenance agility we've gained through this one-button orchestration push has really given us the time to think about and solve or work on solving newer and harder problems. So, like I said, this has not all been rainbows and sparkles. And there are a lot of points that are still painful. If anything, we've come to see where we are now as a state in transition. We are not, I think, where the endpoint should be, but we've opened up or revolutionized, call back to the title, how we've thought about SaltStack in doing so. And the things that really excite us about things going in the future and where this has now gotten our minds thinking is event-driven state machines. Like, we've already started to create the state machine concept with our orchestration, so now let's make it event-driven and take it even further. And Thorium, at least as I saw yesterday, potentially offers us that ability. I'm really excited about that. The health check agent, we're going to actually take our health checks and put them into an agent, and that's a little sub-process we've been working on, or sub-program that we're working on. The big thing for us is, while it's cool to call health checks against the services itself, our monitoring states, our platform validation, these all have basically rewritten the same questions multiple times. Is Zookeeper clustered and happy? So why am I writing a state module to do that and a monitoring script to do that and a platform validation script in a different test suite to do that. So we're actually taking our health checks and we're abstracting them into its own service layer. And then we'll be using that single service layer as a way of having single script authoring, but reuse on multiple ends. And then PyObjects formulas, we're really excited about sort of getting away from the tremendous amounts of Jinja that we have in our formulas. Even when it's light, it still feels too much. And I think a lot of us would be much more comfortable writing things in a pure Python mentality. And then we also have moved away a little bit from the LXC component. So LXC worked except for whenever we needed to put things that required C groups inside of them, which makes sense, right? So Docker, which is a huge part of this platform, couldn't go inside LXC containers. And we had to go to like standard VM stuff. So instead of that, we've actually started working towards building Ansible representations against our OpenStack cloud to just basically provision from our OpenStack cloud a whole bunch of VMs and then do the same paradigms, but just with OpenStack VMs that we're using with some of the LXC stuff. So, questions?
Why did you need to write Salt Orchestrate runner? Why was it able to use stateless for running different orchestration formulas inside orchestration formula?
You can. So the question is, why did we write the Orchestrate runner and not just use state.ls? Since saltmod is a salt state, we absolutely could. The difference is that what state.orchestrate returns is not a standard high state that allows us to tell whether or not all of the states within it have failed, or if any of the states within it have failed. So what it returns in terms of success, currently, state.orchestrate returns true if it managed to run all of them, not whether or not what it ran was successful. So I wanted to dig that data to determine whether or not the states that were run inside state.orchestrate were actually successful and stop if not. I'm sorry, could you repeat?
Oh, so the question was like, if you can't really determine the results, is it possible to do like a separate returner, then parse the detailed information from the returner?
So the question was, would it be possible instead of, if we can't determine the results, to just write the results to a separate returner like Redis or something else, right? And that would be possible, but then I'd have to write something on Salt side to consume what I just wrote into the other returner, and I wanted to keep it basically within Salt if I could. And we don't even use other returners, so I think it would be possible, but you might end up with more engineering tech than it took to write the, I don't know, 50 lines of the extra orchestrate command in the Salt mod.
Why Ansible deploy OpenStack so you can run Salt orchestration?
OpenStack Salt Cloud modules did not work for us. We tried it so much. There are other people in the room who could say more about what went wrong with that. I'm looking at you, Stephen. Like weeks lost and really gave it a hard run at it. But the modules did not work with our version of OpenStack or who knows. Like it's really difficult to target these cloud platforms. We have found that Ansible did a really good job. We're only using it for the provisioning layer, right? We just need something to automate. Give me a bunch of machines under my username so I can go do some other stuff and set up a Salt master. So give me machines, set up a Salt master. That's all we asked.
So that 15 minutes to deploy that data center doesn't include the ops team who has been spending how long to deploy the actual bare metal?
No, absolutely not. Like that is weeks of work, and in fact, that's what limited our. Sorry, I should say this on the thing. Right. So the question was that 15-minute window doesn't include what it took the ops team. And by no means does it include the ops team's work. And that's what limited our window, right? We couldn't get hardware into a data center sometimes until 2 weeks before we had to deliver service on that data center. So we needed to guarantee that we could deploy the application layer and the platform layer within almost no time at all, because inevitably something like a rack will fall off a truck, right? And it did.
So as I understand, this describes how you deliver the infrastructure layer, right? So you can launch a container essentially right in a Mesos platform. So you actually run a real app?
The question is, after 15 minutes pass, and this supposedly brings up a data center, can I run an app on it? And the answer is absolutely yes. In fact, part of the orchestration that I didn't talk about, but was integrated into the Marathon module that we wrote, was deploying our apps. So this was not just a data center deployment for the platform that put up the platform itself. It actually guarantees in that window that we had all of the apps up too. Back there, 1 second. I'll get to you.
One of your slides, you said that the line data is not exposed to Pillar, and then later than that, you showed workaround that. Is that what I just want to make sure that's what you were showing?
Yes. So it's not that the mine data isn't exposed in the Pillar, but the order of events prevents it, and how the fact that the mine compiles on the master affects how that works. Yeah, it's about runtime. So you've got basically a chicken egg syndrome when you have to defer the execution to the state when it's happening on the minion side. And so that's why we do that.
Okay. Have you been able to find how much data you can store in line?
The question is, have we defined how much data we can store in the mine? We haven't pressed it. We limit what we expose in the mine to only what is absolutely necessary, and most of the time that's either a host name or an IP address.
Why pillar of data? Why not grains?
The question was why pillar data and why not grains? This is mostly because we want to be able to control our environments basically through the pillar, and we do a deep merge on that data. The other thing is if things change, we want to be able to apply it in the pillar. The grains data, that gets cached initially when it boots up, and then it's there, it's stuck. And you can do commands that force updates, but it's much easier for us just to rely on the pillar at that point. Other questions? Go right ahead.
So you have some nice modules and runners that you showed to us. Do you plan to open source them, contribute to upstream of SaltStack?
So this is, the question was, do we plan to open source things and contribute upstream? Yes, we want to. We desperately want to. We have a few hurdles. The first is our legal team needs to understand how open source contribution works. We're working with them actively on that. Another is our Salt deploy currently is a little bit behind. Not terribly, but we're a few versions behind, and Salt moves pretty fast. And the other thing that I will openly admit is the style with which we produce formulas is not always popular. It's not a way to introduce people to Salt. It's a way to master Salt. And they aren't always the same thing. And so they can be more complicated or convoluted than I think the average person really wants to use. And I don't think it does us any good to sort of shove that down the throat of the community and be like, here's a better Zabbix module. Yes, it does 10,000 new things and has 200 dials, because that might intimidate other people. And I think there's an open debate currently in the community that cares about formulas as to whether or not they should be simple and used as examples, or whether or not they should be pluggable, reusable architecture. And I don't feel like that's been solved. Yes?
I like the way you're doing it. And then do you happen to have any that are community? Is this an example of one of your formulas that we could?
So at this level, no. So I've been writing Salt formulas for a while, and I have been writing formulas increasingly towards this style through different iterations. So there are older versions that aren't as cool as what we're doing now that are out there. I think PHP NG was one of them, so I'm the guy behind the infamous NG style formulas, which were sort of like experiments that I was doing with Seth on new ways to write them that exposed all the parameters of the state functions down into the pillar, or up into the pillar, I guess. It's a way of looking at it, but I don't think that it's necessarily the end goal. And actually, what it sort of moves us toward, or forces us toward, is writing states in pure Python, where we really want to do things like import and have classes that do, I don't know, standard programming paradigms for us. Because we really want to be able to extend. Because there's so much that we do in formulas that is really similar from state to state and formula to formula. So we're really looking towards using something like PyObjects to allow us to set up abstract base classes and things like that. Go right ahead.
So you have some custom health check thing that allows you to wait for services to health checks plus Consul events that basically allow you to do the same thing?
So the question was, if we're defining all these health checks, and we clearly are using Consul in this particular stack, why didn't we go ahead and use Consul health checks to determine whether or not things were healthy? And the answer is, I need Salt to understand whether or not something is healthy. And the health check module doesn't replace Consul health checks. Those are still present and they're used. But during an orchestration run, I need something to act as a semaphore that will do some retries, go to sleep, do some more retries, and come back, and tell me whether or not we're good to go and continue on our orchestration. Consul health check doesn't help me do that because Salt doesn't know how to interpret the Consul health check response, and that's what the health check module is doing. It's interpreting those responses. And in fact, I think in some cases, we point it to the Consul health check.
But what about Consul events? They allow you to monitor, wait while this service becomes available.
So the question is, what about Consul events?
Well, so with Consul events, you can service X, and you wait. It blocks unless service X.
Right. So the blocking capacities of Consul events. Again, totally cool. And I guess if I wasn't concerned about wanting to reuse this in places where Consul wasn't present in our architecture, or in order to help me bootstrap Consul itself, then it would be a different story. But in this case, where Consul fits in the stack orchestration may not be where I need my first case of a semaphore. So, or I may want to do this to help me bootstrap Consul, which we do. So, okay, so we are pretty much, I think, at time. Yes? Yeah, I think we're at time. If you want to talk more about this, I'm going to be hanging out at the Virtustream booth for the next 3 hours or so. So please feel free to come by. I'll have my laptop. I can show you more there. And thank you all for attending.